Okay, guys, this is for problems 2 and 3. Unfortunately, it's kind of hard for me to do anything with this problem without giving you a substantial portion of the solution. So I'm gonna be that's why I'm forced to be purposely vague here. I don't always like being vague, but if you have questions with this, do as much as you can, and then show up to one of our office hours, and we'll try and work something out. We'll see where you're going and what kind of forces you're getting. Okay, so let me see the markers. You have a truss, and you have forces on your truss, like so. Okay, so the first thing you want to do is you want to come up with, just looking at this, at the loads that are currently in here, you want to find the axial forces in every single member. So when you do that, you have 5 members here. So you want to find the force in AB, AD, BC, BD, and CD. So you want to find the forces in every single member. Once you have that, you want to, in the same table, well, you can arrange this table however you'd like. I'm doing this in a bad order. You can do it in a better order. Just as long as you have everything here, you should be fine. You want to keep track of the length in millimeters. You want everything to be consistent. Your area is given in terms of millimeters, and I do not like working with, so 250 millimeters squared is a very small number in meters cubed. You have to divide this by 10 to the 6 to get meters squared. And I do not like, I prefer working with numbers that are larger rather than smaller. So yes, I convert my length to millimeters. You want to put down the area? It is area, yes, your area in millimeters squared. Your E is given, so you don't need to include that. You can include that here. E equals. And then you want to have extra columns. Okay, I didn't draw this very well, but you guys get the idea. These extra columns I'll leave blank for now. I'll tell you what they are, but so you want to find all these things. Normally you put your force here, you put the force over here, you move these two over by 1, and you move the force over here, so you can put the force over here, and move this one over here, and move this one over here. It doesn't really matter as long as all the values you need are located somewhere on your table. So you have all these, and now for this column. This column is going to be, let's call this FBX, because we want, and we'll call this one FBY. And we'll call this one, what's the last one you want? You want the displacement at D, FDX, horizontal displacement. Okay, so your forces here were due to the axial forces you got in every member were due to the forces in your original problem. To get FBX is the forces in every single member that develops due to a unit load being applied in a direction. So, for example, we want FBX would be the force at B, a unit force at point B in the x direction, i.e. like this. And then with this load, you want to find the force that develops in every single member. And so your FBY is going to be like this by 1. And your FDX is going to be by 1. So yeah, this problem is gonna be, this is one of the drawbacks of using virtual work. Virtual work, it can take a lot. It requires a lot of real work to solve all this. But yeah, let's do this. I know I'm gonna get this question, and people are gonna be like, "Whoa, can we just use RISA?" I think you can use RISA because, okay, so here's the deal. I will say that for this problem, for number 2, you should do everything by hand. And then because you should do at least one full problem by hand. And then I think for the other problems, you can use RISA to calculate your forces. So for example, in RISA, just draw your truss. Because if you have to calculate the forces in every single one of these, this problem alone is solving 4 truss problems with 4 different load cases, and this is even all the work. This is just to fill up your table, and your table is gonna have a lot of values. So yes, I'll say that you should do this one by hand at least. That way you're prepared for the exam, and that way we can justify giving you full credit. And then use RISA later. Okay, to actually get the deflection, at B, I'll do BX, just for simplicity, I guess. You wanna use how do they phrase the equation? They say use the sum of all forces of force times F bx times L divided by AE. So what happens here? What does this mean? Your force, you're going to get some value for force in here. In each one of these members. Each one of these members. If we're only concerned with delta bx, you go to the forces in your bx column. So you have 3 columns here, fbx, fby, fdx. You only want to look at the one that you're interested in. You're interested in fbx. You're interested in delta bx, then therefore you're interested in force bx. From here you want to use the first 3 columns and then this column. So you're using these 3 columns in every deflection case. If I were to look at this, so you see these 2 are the same. So if I'm interested in, I need to move. Okay. My desk is actually very small because this is not in the office. This is at home, and my desk here is very small. But delta by would be the same thing. FBY LAE. So you're just doing you're just replacing whatever you're using, whatever subscript you have here, and using the force there. So your delta by, you're using FBY. I hope I ground that in well enough. But yes, so now you're going to go back up here and you're just going to find the product. So you're going to multiply this force, the force here. So you're going to get F1, F2, F3, F4, F5. You're going to get L1, L2, L3, L4, L5. A is constant, I believe. Yes, A is constant. Bx is going to be F, Bx1, F, Bx2, F, Bx3, F, Bx4, F, Bx5. And so this is going to be F1 times F Bx1 L over AE plus F2 F Bx2 L over AE all the way down, all the way up to 5. Now you're going to say, well, what about the signs? Make tension positive. Make tension positive. Let's use the mind-searing red color. Make tension positive. In all my videos, I think you just look for whatever's highlighted in red, and that should be what's most important. Make tension positive. And if you do that, if you get a negative here, and a negative here, the negative will cancel out, right? And it'll be positive. If you get a negative and a positive, this will become negative. So your signs will take care of themselves. And then if you get a result, so if your delta Bx is positive, it's the same direction as force. If it's negative, opposite direction. Opposite direction. And I think that with that should be fine. Number 3 is very straightforward. So number 3, as a matter of fact, it's so straightforward. I'll use the back of this page. I never use the back of the page because you can see it's already bleeding through. But your delta, number 3 is asking what happens if you change E. Change E. And you'll notice that your delta equation is F times F divided by F times L divided by AE. But the E is constant in every case, right? So I have this in several terms. So I can just pull this out. Right, it's still the same, right? And this is the old. Delta mu, therefore, and then I can express this, I can bring this over here. I can express delta old times E old equals this in parentheses. Therefore, delta nu is equal to how should I say this? And I think this should make sense. So what does this mean? If our E old and our E new are the same, which would be pointless, because I mean you're not changing anything. Therefore, our delta new equals our delta old, right? If our E old is less than our E new, less than, not less than, equal to, less than, then our delta new is going to be less than our delta old. Likewise, if it's greater, it's going to be greater. So you can see that these values make sense. Okay, yeah, let us know if you have any questions. Number 3 is just, yeah, to compensate for number 2 being so complicated, number 3 is very straightforward. So, yes. But yeah, let us know if you have any questions.